Okay, the inverse functions is an old topic, but we definitely need to revisit it here for college algebra. And there are 5 properties of inverses that we need to realize that are still true. So the first property is that the x and the y values are reversed. Now, since the x and y values are reversed, that means that the domain and the range are reversed. So the domain of the original is equal to the range of the inverse. Another property is that the original and inverse, when graphed on the same coordinate plane, are reflections of each other over the line y equals x. So as an example, if I were to graph kind of a half parabola looking like this, and if I thought about what his inverse would look like, this is, whoops, this is the line y equals x, so his inverse would look kind of like this. I didn't do a very good job, but you get the idea. A fourth property when it comes to inverses is that if the original passes what's called the horizontal line test, then that means the inverse is a function. And then a fifth property is kind of a twofer. If you were to put a function inside of its inverse or vice versa, so if I were to put inside of function f his inverse, they would undo each other essentially and just result in the answer of x. And then same thing if I was going to take the inverse function and then put the original function inside of him, it would result in undoing one another and just give you the answer of x. So 2x minus 4, then what is the inverse? So we're going to start by saying we know f of x is really a y, and the first step in finding inverses is to switch the x and y. Switch the output and input. So we're going to set up x equals 2y minus 4, and then because I need my function to be in function notation, I need to isolate the output, the new output variable. So we're going to add the 4, and then last step we're going to divide everybody by a 2. And I'm going to kind of flip this around. Back in Algebra 2, your teacher was fine if you said y equals 1/2 x plus 2 when you simplified it, but because now that we are in college algebra, I'd like your functions, inverse functions, to be represented with inverse notation. So, if I were to graph the original one in blue, I would have started at -4, and then a slope of up to, right, 1. Whoops. Oh, goodness. Okay. A line. And then when I look at the inverse function, I'm going to graph that in red. It goes up 1, right 2. Oops, pretend. It's a little hard to see because I graph so terribly, but this is the line. Whoops. Again. This is the line y equals x. And had I graphed them a little better, you would see they are indeed reflections of each other over that line. Okay, the next part. Again, this is really a y, so if I switch and say x equals y minus 3 quantity squared plus 5, and then I attempt to solve for the output variable, I would first subtract the 5. And then I would square root both sides. Now, this particular function gives us an issue because since the original function was a parabola, when I go to square root to find the supposed inverse, I'm going to end up with the need for a plus or minus technically. They didn't give me any restrictions on my original function, so technically this problem is bogus because there is no existing function, inverse function to the original function. There's a few reasons for that. If we look in your textbook, there's some properties on page 90, and it says that if f is a one-to-one function, then the inverse is formed by reversing the ordered pairs. However, if f is not one-to-one, then f does not have an inverse, and the f to the -1, or f inverse, does not exist. So technically, because our original function is not one-to-one, doesn't pass the horizontal line test, if you think about a parabola, you know, looking like this, he wouldn't pass the horizontal line test. Technically, the inverse does not exist. However, we're going to go ahead and continue solving this. If you square rooted both sides, I'm going to flip this around. You have y minus 3 equals square root of x minus 5. I could put a plus or minus on this because there were no restrictions. And then if I added 3, I'd end up with this. But again, like I said, the inverse doesn't technically exist in this function. I think next year if I teach this again, I'm going to get rid of that question, or at least rewrite it so it asks a different sort of question. Now we talk about one-to-one functions. For a function to be considered one-to-one, then it's going to have to basically pass the horizontal and vertical line test. That's the easiest way to determine if it's one-to-one. So if I think about this problem, they only give you ordered pairs. So when I think about the horizontal vertical line test, it's kind of has to do with the function rule of every x can only have one y, but because it's got to pass both tests, there can be no repeating x's or y's because both tests have to pass. So when I look at this example, I notice right here we've got an x of 3 that repeats, and we also have a y of 2 that repeats. So first question, is it a function? That means every x can only have one y. Well, right here, the x of 3 is paired up with 2 different y's, so no, it is not a function. And since it's not a function, it can't be a one-to-one function. But if I look at the inverse of that example, I would rewrite the ordered pairs by flipping their x and y around. Whoops, that's not what I meant to write. And then the next question is going to ask me, is this a function? So I look at all my x's and I notice that we have a definite problem right here. Since the x's repeat, it is not a function, and no, it can't be a one-to-one function because it's not a function. Is this a function? Unfortunately, no. The 2 is paired up with several y values, so not a function, it can't be a one-to-one function. This does pass the vertical line test, so yes, and it also passes the horizontal line test, so yes, this is a one-to-one function. This passes the vertical line test, it is a function, but it would fail the horizontal line test. So write yourself a little note. That's why it's not a one-to-one function. Number 8, it might be easier if you envision what the graph looks like. This is a line with slope 1/2 and a y-intercept at 2. So something like this. He passes the vertical and horizontal line test, so he is a function, and yes, indeed, he is a one-to-one function. Now for number 9, this is an upside-down parabola that kind of looks like this. Oops, a little better than that. And he does pass the vertical line test. However, he would fail the horizontal line test, so he is not a one-to-one function. Verifying that two functions are inverses of each other is done through composition. So if f of g of x undoes each other, and you end up with x, but also g of f of x has to happen. So let's start with f of g of x. If I take the function g, put it inside of the function f, 3 times something plus 6 is f, and then g goes inside of that. And then we're going to simplify. So I end up with x minus 6 plus 6, which does indeed give me an x. And then going the other direction, g of f of x. Whoops, sorry. Not writing too well today. So we have 1/3 times something minus 2. And then if I go ahead and distribute the 1/3, I do indeed end up with x. So since both f of g of x and g of f of x produce an x, these are inverses of each other. And you'd have to show all that work, of course. So for number 11, they give you function 4 plus x squared, where x's are greater than or equal to 0. Now since they gave me the restriction, the function would only look like this. It'd be half the parabola, the positive part of the parabola. Now he would pass both the vertical and horizontal line tests since they restricted him. So he is able to find an inverse. So let's see if this particular problem is true. So let's do f of g of x. 4 plus something squared, and that something is g, square root of x minus 4. And when we square the square root, they cancel each other out. And 4 plus x minus 4 does indeed result in x. Now if I go the other direction, g of f of x, I take the function g as it exists, and instead of x minus 4, I'm going to put the 4 plus x squared inside of that. Now inside the radical, the 4's will cancel, and I just have square root of x squared, which does result in an x. So yes, these are inverses of each other. Same idea, we're going to algebraically find the inverse. So y equals 3x. We're going to switch the x and y, and then divide by 3. So instead of y equals 1/3 x, I'm going to write it in function notation. Now this next example, if I switch the x and y, I get something kind of interesting. It's a proportion, and I'm going to go ahead and cross multiply. So I have 2 equals x times y minus 1. I'm not going to distribute. The reason I'm not going to distribute is I think, and we could, okay, I'll do it 2 ways. First, I won't distribute. I'm going to go ahead now and I'm going to divide by the x. And I have 2 over x equals y minus 1. And then final step, I would add 1 to both sides. Now this time I am not going to give it function notation just for the sake of space. That's an okay answer. Alternatively, had I distributed the x, I would have added an x to both sides and then divided both sides by x. Now, I would have to accept the answer of 2 plus x over x as an acceptable form, but either one of these are appropriate. Alright, this one's going to take a little bit of work. So we're going to switch the x and y. And this one's going to cause problems for me because now I'm going to have 2 y's in the problem. I'll show you a technique for combining like terms. We're going to cross multiply and get 3xy minus 4x. Actually, yeah, that's fine. And then we're going to cross multiply 2y plus 5 times 1 is 2y plus 5. Now because there's 2 x's in the problem, I want to isolate them. What I'm going to have to do is group them together on the same side and eventually factor them out. So I'm going to subtract this 2y over and get 3xy minus 2y. I'm going to take this 4x, which is not a y term, and add it to the other side. 4x plus 5 or 5 plus 4x, it does not matter. Now because there's a common y in between these terms, I'm going to go ahead and factor the y out, leaving me with 3x minus 2 equals 4x plus 5. And then to isolate that y, if I divide both sides by 3x minus 2, I end up with a lovely answer, which is appropriate. Plus 5 over 3x minus 2. That is the answer I will be looking for. Number 15, cubic function. This is originally a y, but when I switch them, I'm going to solve for y by subtracting the 1. And then final step, to get rid of a third power, I would cube root both sides. There's no need for a plus or minus or restrictions because cube root functions do not have restrictions. And they are 1 to 1. So you could do f to the negative 1, you know, inverse notation. I'll accept either here. 16 is kind of like number 14 earlier. Switching the x and y. You're going to have 2 y's in the problem. And then when I treat it like a proportion and I cross multiply and distribute the x into it, I still have 2 y's in the problem. So in order to isolate them, I'm going to pull the y's on the same side of the equation. And then I could subtract the 7x. Right, this one's going to create sort of an interesting problem. I'm going to go ahead and factor the y out. Now 2x is left minus 1. And it doesn't really say how they want your answer, so I would accept the answer of negative 7x minus 3 over 2x minus 1. But alternatively, sometimes on the ACT, they don't like the lead terms to be negative, so if you were to factor a negative out of this and get 7x plus 3 in the parentheses over 2x minus 1, that would be an acceptable answer. And then to further complicate things, I could take this negative, I could distribute it to the things in the bottom, and that would create a 7x plus 3, and then if I multiplied this by a negative 1, it would change the signs, and then the ACT would flip them around and write it like that. So I don't care which answer you give me, this one is absolutely fine. But that is what we're going to need to know for inverses for this college algebra class.